Oh, hi. All right. Section 11.4, what is conditional probability and how do I use it to solve problems? Uh, this this section is probably the most useful. Like it applies the most to real world situations and kind of brings together everything that we've been doing in chapter 11. So I kind of like it a lot. As a quick little warm up, we're going to start with what is the probability of drawing two cards out of a deck and getting a queen followed by a 10? Well, there are 4 queens in the deck and there are 4 10s in the deck. So I have 4 out of 52 for the first card being a queen, but the next card being a 10 is 4 out of 51 because I have, unless it explicitly states I'm replacing the queen that I drew first, we have to assume that that is not the case. So what we're going to do here is, sorry, cords everywhere. We're going to go to the calculator. 4 out of 52 times 4 out of 51. 4 out of 51. Let's go to just hit enter right away, and then we'll go. So not very good. Math enter, enter. So 4 out of 663, or 0.006 is the probability that I roll queen first and then 10 seconds. How about the probability of drawing a red card followed by a black card? Well, red cards, there are 26, and black cards, there are 26. So this would be 26 out of 52. And then again, unless it says I'm going to replace it, I have to assume that I'm going to go down by 1. So it's 26 out of 51. 26 out of 52 is just 1/2, so I'm going to start with that. Times 26 out of 51. 0.255, essentially. 0.255. Or as a fraction, that probability would be 13 out of 51. Okay, so a couple of, technically these are and probabilities because it's red card and then a black card. So yeah, there's that kind of the multiple events thing that we talked about in 11.3. All right, conditional probability deals all with dependent events. So dependent events, again, just meaning like one event happening means that the probability of the other event is affected in some way. Either it goes up or it goes down. So to look at that, let's look at that second warm-up example. Okay. What is the probability of drawing a red card followed by a black card? So if we just think about the probability of drawing a red card, that's 26 out of 52, or 1/2. If you ignore, all right, so just like clean slate, regular deck of cards, a complete deck, what's the probability of drawing a black card from a fresh deck of cards? Well, that's 26 out of 52, or also 1/2. Well, then obviously the fact that the red card was pulled from the deck has now changed my sample space from 52 down to 51. And so that's what we call a given event. Okay. So in mathematics, we use this vertical bar to talk about given events. So this reads the probability of B given A. And when we say given A, it's basically saying what's the probability of event B happening, knowing that event A has occurred. Okay. So if we think about this, what is the probability of drawing a black card given that we have already drawn a red card? Well, we saw in the warm-up that that is 26 out of technically 51 because the red card coming out has shrunk our sample space. Okay. And we know these events are dependent because these numbers, these probabilities are not the same. Okay. So event A occurring has actually increased the chances of drawing a black card next because there are 26 black cards, but now there are 1 fewer red cards in the deck. So the big thing to take away from this, that tall bar means given. The event that comes after the bar is the So let's break this down just a second. This has already occurred. And B is what we want to occur, want to happen. Okay. So whatever event comes after the bar has already occurred. A way that we answer a lot of these questions is with what are called contingency tables or two-way tables. It allows you to report feedback on multiple categories in one single output. In section 11.3, we talked about a problem where it was, do you play a musical instrument, or do you play a sport, or do you do both, or do you do neither? And this is one way that we could show a contingency table, okay, or one way that we could show all that data in one spot. So just kind of run you through here. Do you play a sport? Yes, is all of these people right here. Okay, so in total, there are 150 people that play a sport, right? Between those 150, some of them also play a musical instrument, some of them don't. This column right here represents all the people that do not play a sport. So whether or not they play a musical instrument, we don't know. Well, we do because it's separated, but all of these people, these 350 total humans, fall under the category of not playing a sport. Okay. Then, of course, if I read side to side or across the way, these 200 people would be all of the people who do play an instrument, right? Because they all answered yes to the question, do you play an instrument? And then these people down here would be the 300 that do not play an instrument. Okay. Most of the time, these contingency tables or these two-way tables do not come with the totals on the outside, but a lot of times it's going to be helpful for you to answer probability questions if you have the two-way table, if you have the totals added on to the end there. And of course, like, you could also add one more, like, how many total people are we talking about? Well, if I add up the people who play a sport and the people who don't play a sport, I get 500. And I should get the same thing. Here, right? If I add up all the instrument players and the non-instrument players, I should get 500 as well, which we do. So we're going to use this table to answer a couple questions real quick. So determine the probability that a student chosen at random plays a sport. Now, we don't know anything about this student, okay? So we are drawing from all 500 students, okay? Of the 500 total students, that's our sample space, what is the probability that I pick someone that plays a sport? Okay? Like we said, if they play a sport, it is one of these 150 people. This question is not asking about their musical instruments, whether or not they play it. All we're asking for is what's the probability that I pick someone who plays a sport, and that is 150 out of 500. This can then be reduced to 3 out of 10 or 0.30 or 30%. Okay, so what's the probability that someone plays a sport? That's total. Next question, what is the probability that someone does not play an instrument? Again, I'm drawing from all 500 characters, all 500 people. What is the probability they do not play an instrument? Well, for playing instruments is over on the left side here. All the no's added up make 300. So 300 people answered no to that question. So 300 out of 500 is my probability. This is 3/5 or 0.60 or 60%. So I have a 60% chance of choosing someone who does not play an instrument. The next question is why these tables are useful and why we use these contingency tables. What is the probability that a student chosen at random plays a sport given that they play an instrument? Okay, so what's key there is whatever words come after the word given. given they play an instrument. Okay. What that means is I know I'm picking someone who plays an instrument. That is given information about them. So what that means is I am only looking at these people right here. Right? These 200 people are the ones that answered yes to the question, do you play an instrument? So that given event now shrinks my sample space. I'm not drawing from all 500 people now. I'm only drawing from the 200 that responded yes to playing an instrument. What is the probability that I pick someone who plays a sport? Well, of those 200, these 50 also play a sport. So this would be 50 out of 200, which is 1/4, which is 0.25 or 25%. Okay. What's key here, and this is, we're going to keep hammering this stuff, is if you see the word given, your sample space is not everybody now. You are only looking at a certain characteristic or people that match a certain criteria. Okay. The first two questions didn't use the word given at all, so we were picking from all 500. Okay. So let's look at some of these other ones. Gender breakdown of college students in 2005 is as follows. We have a table on the left side, males and females in 2-year colleges, 4-year colleges, or in grad school. Okay. You'll notice that up here it says in thousands. So it's not just like 1,800 students were in, 1,800 males were in 2-year colleges. That's actually 1.8 million. For the sake of probability, that's not really going to matter because all of this is we're going to divide and we're going to get decimals anyway, but just be aware of that. So one person chosen at random, find the probability that they are female. Now, there's no given event there, which means I am picking from everybody. So I need to take some time right now and figure out some totals. So 1866, I'm going to go to the calculator here. I'm going to add up 1866. I'm going to add up all the males first. Plus 4324 plus 1349. It gives me 7539. So just to give you a look at what I'm doing here, right? This gives me the total of all the males that have that were in college in 05. Then I'm going to take the females and add those as well. So 2462 plus 5517 plus 1954 is 9933. And then I'm going to go ahead and add straight across. So the 2-year colleges, there are 1,866 males plus 2,462 females, or thousands. So that's 4328. Might seem like tedious work or unnecessary, but this stuff is super important so that we can answer these next questions very quickly. 5517. So 4-year colleges, that was 9841. And finally, in grad school, there was 1349 plus 1954. That's 3303. And then I'm going to get a grand total here real quick. So it's 7539 males plus 9933 females. 17472. 17472. So all that calculating to then expand my table so it looks like this. Okay. And again, these numbers I'm reading across. So how many total people were in 2-year colleges at that time, that would be the 4328. Okay. How many females were in college back then? That's the 9933, which is 9.9 million. Okay. So find the probability that one person chosen at random is female. Okay. So again, since there's no given event, my sample space is going to be everybody. So it's 17472. And then what's the probability that they're female? That doesn't say anything about like they have to be in grad school or they have to be in a 2-year college. So I'm going to take the total down here of all the females. So it'll be 9933 out of 17472. So 9933 divided by 17472. and I get 0.569. Okay, so this is going to be 0.569 or 56.9%. Again, I could probably go math, enter, and see if that reduces. 473 out of 832, or 73 out of 832. So there's that. Next question is, what is the probability that I choose a female student given that they are in grad school? Okay, and this is why we did all that work to total all that up. The given event is they are in grad school, which means I am only talking about this group of people. Okay, I'm not talking about every college student. I'm just focused on the grad school people. So my sample space now is 3,303. Of those 3,303, how many are female? And that's where the 1954 comes in, the 1954. So 1954 out of 3,303. And that gives me 0.592, or, okay, so that fraction can't be reduced because the math enter gave me the same thing. So about 0.592 or 59.2%. So it's kind of interesting, and whatever. We're not analyzing this data real closely, but if you look at the first two answers, we had a 57% chance of choosing a female from all college students, and that probability rose when we talked just about grad school students. That rose up to 59.2%. So you're slightly more likely to choose a female from a random group if you know they are in grad school. Finally, let's flip the script a little bit. What is the probability of picking a student who is in two-year college given that they are male? Okay, so now male is the given event, which means I'm working in this column right here. These are all the males. Okay, so out of 7539, which are all the males that were in college, what's the probability that I choose someone in a two-year school? So it's going to be that 1866. So 1866 out of 7539. 1866 out of 7539. I get 0.248. 0.248. Or as a fraction, do I get the same thing? 622, or 622 out of 2513. Okay. So this then gives us that final answer. So again, just more practice with the given probabilities. This is a formula out of the book. I'll be honest, I'm not a huge fan of it. Like, you can, most of the time you can think your way through this stuff instead. But if you wanted to calculate the probability of a given event, you are going to take the probability that both events occur. Okay, so the probability of B and A, and then you are going to divide by the probability of the given event. Okay. Again, it's a conditional probability formula that's in the book. Most of the time, given events, it's easier to just, if it's in a table, or soon we're going to see a tree diagram, it's easier to just kind of like focus in on what you're doing and not worry about trying to remember a formula. Okay, I know it says using the conditional probability formula, but go ahead and just try this on your own. So 50 people were asked whether they pay their bills online. Here are the results. See if you can answer those two questions. I'm going to go ahead and total these up. So the online payments are 36 total. By mail is 14, and sure enough, that adds up to 50, which is great. Male respondents were 20, female respondents were 30, which also adds up to 50, so I know I did my math correctly. What is the probability that someone pays online given that they are male? So the given event is male, so I'm working with just these 20 respondents. So out of 20, how many of them pay online? 12 of them do, which is divided by 4, that's 3/5, or 0.6, or 60%. And then what is the probability that I choose a female, given that they do use the snail mail to pay. So given that they pay by mail, is 14 out of 14. 6 of those are female, so that's 3 out of 7, which is like 0.43. 0.4285, yep, so 0.429. 0.429. Okay, so there's that. Last thing we got to talk about is a tree diagram, and these are, they get a little interesting, and they get, if you're not terribly organized, they can get real messy, but we're going to see how we can find conditional probabilities very quickly from it. So a class of high school juniors were asked the following question 10 years later. Okay, so if you're a junior now, imagine that we ask you this question in 10 years. Are you happy with your current job? Okay. Of those that responded, so 85% of the juniors graduated high school. Okay. And then from here, of the high school graduates, 90% were happy. So that's saying if you did graduate high school, then 90% of those juniors were happy with their current job. And then of the non-graduates, so of those juniors that did not go on to graduate high school, 60% of them were happy with their current job. Okay. So we're going to display all this information using a tree diagram. Okay. So that first statement that we're given, that 85% of the juniors graduated high school, how we're going to do this is we're going to literally just draw a sideways expanding tree. So this first branch is they graduated, or the other option is, of course, that they did not graduate. And then at the beginning of the tree, I'm going to label this juniors because those are the people who are asked. So juniors here. Oh boy. Okay. And then I'm going to label each branch with the probability that a student falls under that category. So of all the juniors, 85% graduated. This is not given, but we can infer that of those then that didn't graduate would be 15% of the students. Okay, so 85% graduated, 15% did not. Of the high school graduates, so let's assume that you've made it across to the graduation end of it, 90% of those people were happy with their job. So from the graduated, I have two choices. Either you're happy with your job or you're not happy. Okay. Of those that are happy, this was a 90% probability, which means that 10% did not, or would 10% of those that graduated were not happy with their job. You'll notice that these are all in percentages. The problem gave all these in percentages, but I am writing them as decimals. That's not by accident, because we're going to be doing some multiplication with these numbers soon. And if you have percentages and you try to multiply, then it's going to give you very wrong numbers because it gets way over 100%. So then the final statement was of the non-graduates, 60% were happy with their job. So same two branches coming off the non-graduates, happy or not happy. And we see that 60% were happy, which means that 40% were not happy. Okay, so here's a tree diagram that we have for this information. Now, I want to label a couple of things here. Okay, so this is the probability that a student graduated is 85%. What's the probability that they did not graduate? So a non-graduate is 15%. And this is why we use these tree diagrams, because this diagram actually gives me this gives the conditional probabilities. So this is so 0.9 is the probability that a student is happy given that they've graduated. right? And I know that they've graduated because it's after the graduated like branch of this tree. So down here, the 0.1 would be the probability that they are not happy given that they have graduated. So that's that one. I'm going to shrink this down and put that right there. Okay. The 0.6 then would be the probability that a student is happy given they did not graduate. And finally, this 0.40 is the probability that they are not happy given, or if I know that they did not graduate high school. Okay, so this second tier of branches actually tells us the conditional probabilities directly because it's after the first set of values. Okay, so I'm actually going to take this thing and copy it so that we can, unless I already did that. Did I? Nope. Okay, so I'm going to copy this thing and then we'll use it to answer some questions. Copy that. Okay, I'm going to just paste this down here, maybe. God, it's got to be fun to watch old men deal with technology. All right. What is the probability that someone is happy given they graduated? Again, now this is kind of nice because I can just look at this second set of branches, right? These are all my given probabilities right in here. So I want to know what's the probability that someone's happy given that they graduated. Well, happy given that they graduated is right here, so that's 0.90. Okay, so 0.90. Now this is, the next question is where we have to do some thinking. What's the probability that a person chosen at random graduated and is happy? Now, what's key here is that the word "and" does not tell me anything about that person. I don't know for a fact that they're a happy person. I don't know for a fact they graduated. This is just saying if I pick someone at random, what is the probability that they both graduated and they're happy? So to find the "and" probabilities in a tree diagram, we have to go ahead and multiply the branches together. Okay, so if I want to know what's the probability that someone graduated and they're happy, I'm going to take the 0.85 and the 0.90 and multiply those together. So 0.85 times 0.90, that will give me the probability that both events have occurred for that person. So it's 0.765. So I'm going to come back here. Okay. And go with this. So that is the probability that both have occurred. So 0.765. What's the probability that someone is chosen at random is not happy? Okay. Again, with these problems, it's kind of annoying. The less information you have, the more work you have to do. So what's the probability that someone is not happy with their job? Well, there's two branches here that constitute not happy people, right? There's the ones who graduated and aren't happy, and then there are the ones that did not graduate and are not happy. So what we have to do is we have to find those two individual branches, and then we have to add them up. Okay. And again, to find the end of each branch or to get to the end of that path, I have to use multiplication. So here I'm going to take 0.85, which is the graduation probability, and multiply by 0.10. Okay, that gives me 0.085. So that's the probability that someone is graduated and not happy with their job. And then down here, I go to the 0.15 times 0.40. That gives me 0.06. So there's a 6% probability or 0.06 probability that someone didn't graduate and they're not happy. So now to find the probability of just someone not being happy with their job, I have to take these values and add them up. So 0.085 plus 0.06, and that's 0.145. So you have a 14.5% chance of choosing someone at random that is not happy with their job. And then finally, the last question is easy because it's a given. What is the probability that someone's not happy with their job given they did not graduate? And that we can see is right here, that 0.40. So that's a simple answer to a simple question, 0.40. Okay. These tree diagrams are tough and they take a little bit of practice. But once you get the hang of it, it's a really useful way to display data because it allows us to get a lot of information across very quickly. It's going to wrap it up for 11.4. I know it was a longer video, but hopefully some of this stuff makes sense as we get close to wrapping up our probability unit.